Welcome to The Explainer. Today, we're taking a trip back in time, back to the very roots of artificial intelligence. Think about it. Before all the buzz about big data and neural nets, how on earth did we first try to teach a machine to think? This is the exact question that kept the pioneers of AI up at night. I mean, if you can't learn from experience the way you and I do, what's left? How do you even begin to build a mind from absolute scratch? Well, the answer is pretty fascinating. You build a mind that doesn't guess, that doesn't predict. Instead, it deduces. We're talking about the world of logic-based AI, where thinking is this beautiful science of pure, crystal clear reason. Okay, so how does this whole thing work? Here's the plan. We'll kick things off with a language of logic. Then we'll see how that language creates the building blocks for reasoning, how an AI can use it to find new truths, get its knowledge organized, and finally, how it all leads to taking action in the real world. All right, first things first, the language of logic. You see, if you want a machine to reason, you absolutely have to give it a language that is perfectly 100% clear. There can be zero room for ambiguity or mistakes. And that language is logic. It's this complete formal system. And it really comes down to three key parts. You've got syntax. Think of it as the grammar rules. Then there's semantics, which is all about what the sentences actually mean. And finally, the inference procedure. This is the real engine, the part that figures out what new things logically follow from everything it already knows. Okay, so let's get practical. How does this actually work? We're going to start with the simplest possible building blocks, just basic statements about the world. This level is what we call propositional logic. And it's all about simple statements, or propositions, that can only be one of two things, true or false. That's it, no gray areas. For instance, the statement, "It is raining." It's either true or it's false. In the world of pure logic, there's no such thing as kind of raining. Okay, now this is where it gets really cool. We take those simple true or false statements and we start combining them. To do that, we use these things called logical connectives. They're basically like and, or, and if-then in English, but for math. See that wedge symbol? That's and. The V shape, that's or. And the arrow means if-then. And just by stringing these together, you can start to express some really complex ideas with total pinpoint precision. But, just like any language, you can't just mash symbols together randomly and expect it to make sense. A statement has to follow the grammar rules to be meaningful. And in logic, we call a grammatically correct sentence a well-formed formula, or WFF for short. So, the example you see on top, that's a valid sentence our AI can totally understand. The one on the bottom? Yeah, that's just nonsense. So propositional logic is a great starting point, but it's got its limits. I can't really express general rules about how the world works. For that, we need to level up to something called first-order logic. This is what lets us talk about objects and what they're like. So instead of just a simple fact, like Socrates is mortal, we can now make a big, universal statement like all humans are mortal. And that, right there, is a massive leap forward. It's how we start giving an AI general knowledge it can apply anywhere. Okay, so let's recap. Our AI has a language and it has some facts about the world. But how does it actually use that knowledge to figure out something new, something it hasn't been told directly? Well, this is where we get into the art of inference. Inference is really the engine of all this logical reasoning. It's the process of taking all the stuff in what we call the knowledge base, or KB for short, and using a set of formal rules to come up with new conclusions. I like to think of it like the AI is playing detective. It has a bunch of clues, and it's using its rulebook to connect the dots. And one of the most powerful, but also just beautifully simple rules is called modus ponens. Now, that's a fancy name, but it's for an idea you and I use constantly without even thinking about it. It just says, if you know that A leads to B, and then you see that A actually happened, well, you can be darn sure that B is true too. It's pretty much the bedrock of all logical deduction. All right, let's put our AI to the test, shall we? Here's a little challenge. On the screen is its knowledge base, just 5 simple facts that it knows for sure are true. And here's the question we're asking it. Based only on those 5 facts, can you prove that the statement R must also be true? And here's how it pulls it off. It's so elegant. A proof is nothing more than a chain of logical steps. The AI starts with what it knows, the premises. So in step 3, it sees it knows both S and T, so it applies the AND rule to conclude S and T is a new true fact. Then check out step 5. It uses our old friend modus ponens on fact number 2 to prove Q.
It just keeps going like this, one logical step after another, until boom, in line 9, it proves R. There's no guesswork, no hunches, just pure, clean deduction. Okay, but let's be real. For an AI to reason about the actual world, it needs more than just a random list of facts. It needs, well, it needs a map. A structured map of all the concepts and how they relate to each other. And that is where something called an ontology comes into play. The best way to think about an ontology is like a super detailed dictionary and encyclopedia all rolled into one, but built specifically for a machine. It doesn't just define what things are, it defines how they're all connected. For example, it might define that a human is a type of animal, and an animal is a type of physical object. The whole point is to remove every last bit of ambiguity. And these things, they can get incredibly vast and complex. What you're seeing here is just a tiny little glimpse of a high-level ontology. It's building this massive hierarchy for literally everything, from abstract concepts like numbers all the way to physical things like animals. It really is a blueprint of all knowledge. And this isn't just academic stuff. Here's why it's so important in the real world. Think about medicine. An ontology can define the exact relationships between different doctors' specialties. That way, computer systems can share patient info without making a single mistake. Or in business, it can map out an entire complex process, defining the who, what, when, where, and why of every single step. So you might be wondering, what's the end game here? What's the point of all this? Well, we're not just building a system that's a know-it-all. We're building a system that can do stuff. All this abstract reasoning has one ultimate goal: to enable intelligent action. So this whole logical framework that we've been putting together, the language, the inference rules that organize knowledge base, it all comes together to allow for one crucial thing: planning. An AI can use this logic to think ahead, to search through all the possible futures and find the perfect sequence of actions to reach its goal. And it does all of this before it even has to move a muscle. But, and this is a big but, here's the catch. It's one thing to have a perfect, logical plan. It's another thing entirely to actually execute it in the real world. Because the world is messy, it's unpredictable. A self-driving car can't just pull over and pause to run a 9-step proof when a pedestrian steps out. No way. It has to make decisions in milliseconds. And that is the fundamental challenge, right? Bridging that massive gap between the clean, perfect world of logic and our chaotic reality. And that kind of leaves us with a final thought to chew on. In today's world of AIs that can sometimes be unpredictable, maybe even a little unexplainable, there's just something so powerfully elegant about these classic logic-based systems. Their reasoning is totally transparent. Their conclusions can be proven step by step, and their behavior is certain. And maybe, just maybe, there's a really important lesson in that certainty that we shouldn't be so quick to forget.